Most of the things we encounter in everyday life are not elements. They're compounds or mixtures of compounds. Free atoms are quite rare in nature. So a compound, as we talked about yesterday, is different from a mixture of elements. In a mixture, you can have varying amounts of the two parts of a mixture. In a compound, the ratio of atoms of one element to atoms of the other element is always the same. It's a fixed ratio. So we say it has definite proportions. In a mixture, the proportions can vary. So here we have an illustration of a mixture of hydrogen and oxygen and a compound formed by hydrogen and oxygen. In this balloon, we have a mixture of hydrogen and oxygen gases. You can vary that mixture. You could have a lot of hydrogen or a little bit of hydrogen. We look at the particles in this gas and we see two different kinds of particles. We have hydrogen molecules and we have oxygen molecules. The particles are not all the same. That's one of the keys, the clues that this is a mixture. Here is a balloon filled with water. The first time I saw this picture, I'm like, what the heck am I looking at? This is a water balloon, and they took the picture just a split second after it popped. And so the red here is the latex balloon contracting, and the water hasn't had a chance to fall yet. So it's kind of a cool picture. The water also contains hydrogen and oxygen, but all the particles are the same. They are water molecules, and there's always one oxygen to two hydrogens. It's a definite proportion. This is a compound. This is a mixture. Any questions? So this idea of constant composition, definite proportions, came up back in the late 1700s. So Joseph Proust was the first one to formally state this idea, that elements combine in fixed proportions. So that's called the law of constant composition. All samples of a given compound have the same proportions of their constituent elements. So water that you pull out of the Kings River has one oxygen, two hydrogens. Water that you pull out of the Nile River in Egypt, same composition. The Atlantic Ocean, same composition. Dig down deep at the North Pole into the ice cap, melt some of that water, analyze it, same composition. Water is water, it's always the same. So if we took a sample of water, and a sample that weighed 18 grams, and we decomposed it, it's a compound. It can be separated into its elements by a chemical process. We would find that you'd get 16 grams of oxygen and 2 grams of hydrogen every time if you start with 18 grams. So if we look at the ratio of oxygen, mass of oxygen to mass of hydrogen, we get a ratio of 8. That ratio is constant for all samples of water. All compounds show this constant composition because they're formed from atoms combined in fixed ratios. Because it doesn't have to do like with baking where you have this amount of flour and this amount of sugar and you put them together. It's like building things out of Legos. It has to do with the individual pieces. It's one oxygen atom, two hydrogen atoms. Since the numbers of particles are the same, then the ratio of the masses is always the same. So if we have two samples of carbon monoxide that we got from different sources and we decompose them into their constituent elements, it says that one sample produces 4.3 grams of oxygen and 3.2 grams of carbon. And the other sample gives 7.5 grams of oxygen and 5.6 grams of carbon. And the question is, are these results consistent with the law of constant composition? So what we want to look at is the ratio, of the masses. So sample 1 has 4.3 grams of oxygen and 3.2 grams of carbon. And sample 2, well, there's not going to be enough room down there. We'll do it over here. Sample 2 had 7.5 grams of oxygen and 5.6 grams of carbon. We want to look at the ratio either of oxygen to carbon or carbon to oxygen. It doesn't matter as long as you do the same thing to both of them. I prefer numbers that are greater than 1. So I'm going to look at this and say, well, there's more oxygen, so I'm going to look at the mass of oxygen to the mass of carbon. So I'm going to do an oxygen to carbon ratio. So grams of oxygen divided by grams of carbon. So there's 4.3 grams of oxygen to 3.2 grams of carbon. So that's going to give me a ratio of 4.3 divided by 3.2, 1.34375. This is a ratio. Look what happens to the units. Grams cancel grams, and they go away. Are these exact numbers, 4.3 grams of oxygen? No, those are measurements. Those are masses. It was measured. So we should consider significant figures when we look at this ratio. So this has 2 sig figs and 2 sig figs, and when you take 2 and divide by 2, you go with the smallest, which is 2. So this should have 2 sig figs, and so we'd say that the ratio is 1.3 for that one. Now I'm going to do the same calculation for the other one. I'm going to do grams of oxygen to grams of carbon. So the numbers are different here. There's 7.5 grams of carbon to 5.6, I'm sorry, grams of oxygen to 5.6 grams of carbon. Because this sample was larger. The starting sample was larger, so we got more carbon and more oxygen, but we're going to see that the ratio is probably the same. So 7.5 divided by 5.6. So my calculator is telling me 1.33928, blah, blah, blah. If you look at this number and that number, you might say, well, they're close, but they're not exactly the same. But there's uncertainty in these because they're based on measurements and not very great measurements to start with. Again, 2 sig figs, 2 sig figs. We should round this to 2 sig figs. So we get 1.3 as the ratio for this one. It's the same ratio. Does this support, is it consistent with the law of constant composition? Yes, it is. Any questions?